Okay, now we're recording. Like I said, we finished fluid statics chapter. So you guys should know already about how pressure distributes over inside the fluid, within the fluid, uh, and how that pressure depends on the weight of the fluid, and how that pressure distribution create forces on on the walls, on the bottom, on submerged bodies, and how those submerged bodies can actually float, and how that flotation can be or cannot be stable. Uh, all of that should be more or less clear. If not, is there any questions that you might want to ask now? Okay, so I'm gonna assume it's all super clear. So we're gonna start in this new unit. Like I said, it won't get into the next week midterm, um, but we need to keep to keep advancing. So I'm thinking that you should be able to see the slides, and you also should be able to download them from Canvas if you want to follow along. I'm going to switch between the slides and the whiteboard, so it could be handy if you have the slides, at hand. I'm thinking that we're going to take less than an hour to cover the slides. Then I'm going to leave a few minutes, maybe 20, 15 minutes at the end, to introduce a bit of what you're going to have to do in the homework, the coding homework related to pressure forces. So I think I recommend you to stay and have a look at that if you can. Uh, but yeah, we might be finishing a bit early today. So if we have that spare time, we can also answer questions regarding pressure, forces, and maybe do a couple of exercises if you feel like. Okay, so let's get into kinematics. So this is more or less how the chapter is split. Today we're only gonna see the first few points, actually up to point 4, but we're gonna get into the basics of kinematics. So kinematics has to do with velocities, right? Whenever we say this is typical physics. We already studied the static part. Now we're going to get into the kinematics, which has to do with velocities, and at some point we're going to get into dynamics, which has to do with the actual forces driving motion, right? But for now, we're only going to be happy describing the flow, but we're not going to go into why the water or the fluid is flowing. Okay, and here you can see a couple of pictures of flows. You can see smoke going up and doing this. Hello, hello. Can you hear me now? I'm being
Yes, much better.
Yes.
okay. So this, yeah, this is a new headset, so I'm just still testing it. So if you have any problem, just let me know. Maybe I can switch to the old one. So here you have a couple of examples of flows, and actually, maybe can you see my hand here, my mouse hand? So here you have laminar flow, which is very orderly flow, and here you have turbulent flow, which is flow going everywhere. We'll get into the specifics of that later on, but you've all been familiar with smoke and with pressure. So when you see a flow, you understand what we're talking about. And the key concept here is that we're going to consider the flow to be a continuum. I mean, that means that we're not interested in describing the motion of each particular molecule, for instance, molecule of water, but how we describe the motion of water. And water is just a collection of molecules. So molecules, we know they're not joined to each other, uh, but these parcels of fluid, they do touch each other, and we can assume that the properties of each of these little parcels change smoothly from one position to another, and that's what's called continuity. And it's a classic assumption on most physics, right? So if you want to analyze, heat transfer, or forces or pressures or velocities in this case, we're going to assume that the fluid works as a continuum, right? And that will let us use differential tools, differential partial derivatives and integrations, because we know that all properties are smooth and change smoothly as we move through the fluid. Okay, so that's a big assumption here, that the flow works as a continuum, and it works pretty well. So typically, we can think, if this is the case, we can think that all parameters can be represented as a field. Okay, and a field means that whatever parameter, in this case is pressure being highlighted, uh, the pressure is a function of location, and location, we're talking about location in any point of space, so it depends on x, y, z, but also is a function of time. So you see, pressure in this case is a function of four coordinates, right? Three in time and one, three in space and one in time. Uh, but we know that pressure works. We know from Pascal law the pressure works the same in every direction. So we only need the magnitude, the scalar, to represent pressure. But that's not the case for other variables. In particular, it's not the case for velocity. So um, I'm gonna stop sharing the screen, but please do follow along the slides, because I think it's easier if I just work uh, on my whiteboard. Okay. So basically, let's say if we have, you know, a Cartesian coordinate system, where this is x, y, and z, and we have a parcel of fluid. Okay, a very small unit of fluid. Okay, so the location of this parcel of fluid, or if you've done vectorial mechanics, this is pretty standard stuff. The location of this is this vector r, which you can express it. R is you know some magnitude in the y hat direction, some magnitude in the j hat direction, and some magnitude in the k direction. This is the same as x, y, and z axis, right? And let's say this parcel of fluid is moving through a line, or through a is following a certain direction. So it has a velocity, right? But velocity is also a vector. So velocity is also a vector, and by convention, we normally call the magnitudes in each direction, we call them u in y times uv in j times w in k. This is just convention. This is the velocity in x, and velocity in y, and velocity in z. These two are horizontal velocities, and this one is the vertical velocity, right? So velocity is a vector, in contrast to pressure, which is a scalar. It doesn't have uh, direction. Pressure works in every direction. Uh, but since we also know the position, actually velocity is the derivative of the position. Okay, and on kinematics, we're gonna get a, a bit heavy on derivatives, but it shouldn't be anything that you haven't seen before. So basically, as a definition, the velocity is the derivative of r with respect to time, right? Uh, so u is actually the derivative of this value x. Let me just rewrite this to be consistent with. So this we're going to call x, y, and z. And these are going to be the axis. So this is more, these are more consistent. All right. So basically, u is going to be the derivative of x, v is going to be the derivative of y, w is going to be the derivative of z. And the magnitude of v is going to be the magnitude of each of these components. So it's going to be the square root of u squared plus v squared plus w squared. Okay, this is just trigonometry. It's pretty standard, right? So given this given this definition, we can look at different characteristics of fluid. And please be aware that uh, v depends on x, y, z, and time. So in the same point, you can have a different velocity along the time, and as as long as you move across space, you can have also different velocity. Okay, uh, and basically we separate this in two categories: if flow changes over time, and if flow changes on space. And what we normally say is that if the flow changes over time, we call it unsteady. And if it doesn't change over time, we call it steady flow. Okay. So we're gonna have, let me just write down here. So we're gonna have steady and unsteady. And let me close my Outlook. And we're gonna have uniform if it doesn't change in space, and non-uniform if it changes. Okay, so these guys are related to changes over time, this bunch, and this other changes uh, over space. Space considered as the vector of space. Okay, so this is typical. You can read it on the book. It's pretty, but I think it's really nice if I show you some examples. So let me share my screen. Okay, so you've probably seen this or something similar to this. This is a tap, and you have this red liquid flowing out. Actually, it doesn't look like flowing, right? It looks kind of froze, or I don't know. It looks like plastic. But here, this guy is touching it, and actually, you can see that it is actually flowing. This is a typical example of steady flow. It is steady because the characteristics of the flow don't change over time. So it doesn't matter what moment you're looking at this, the flow is the same, and the field of velocity is the same, and the field of pressure is the same, right? Until you go and perturb it like this, okay? And steady flow, we're gonna see down the course, uh, is something that doesn't happen very often, but we use it as engineers to make computation because it makes our life easier, okay? So let me show you. Here's a nice example of open channel flows. This is a classic educational video from the 70s or so. But here you can see this is an open channel. So it's a canal somewhere in the UK. And it has an interesting pattern of flow. And here some people are trying to do an experiment on the lab. So you can see here there is a lab, there is a canal, and they are filling up with water, meaning that there is water coming in. And at some point, the water starts to flow over this structure. The structure is called a weir. You can see water flowing out. During all this time, this is unsteady flow because the flow is changing over time, right? And also, it is non-uniform because the velocity here, for instance, is different to the velocity here. So it's not uniform. But at some point, if you keep your flow coming in constant, then you develop a constant shape, right? And then the flow is steady. At that point, the flow is steady. So the derivatives against time are zero, are null. Of course, it's non-uniform, but uh, and I think that was it with this guy. And here, this is a similar video, similar canal. Uh, I think it was around here. Yeah. Basically, here you can see there's water coming in. Here, the guy put a, let's say, a wall. So he's putting water here. Here, this structure is a diffuser, so water doesn't move around too much. Here, you should be able to see the canal. The water along the canal should have the same height, the same depth. So in this case, you can see water is flowing, but it's not changing in time. So the flow is permanent. This flow is pretty uh, uh, what's the name? It's pretty turbulent. You can see, but overall the levels remain more or less the same. So this is a classic example of steady flow, and in this case, in this part from this on is pretty uniform. I mean, below the gate. Yeah. Now what happens is here is talking about energy that we'll see later on. I'm going to reuse this video. Here what happens is that he will open the gate soon, I guess. And once he opens it, the flow stops being steady, and actually a flood wave comes down the canal, right? I miss it. So here he should open it now, and you see the flow changes over time and on space. So during the opening of this wall, you have unsteady flow and non-uniform flow, right? But if you keep it, if you leave it flow for long enough, you return to a steady state because this thing has to be in equilibrium. So it returns to a steady state until you perturb it again. So now he puts a weird or a seal, it's called this thing. He's going to put it on the floor, and what's going to happen? The flow is going to change up until it reaches a new equilibrium. And while it changes, the flow is going to be unsteady until it reaches a new equilibrium, and then it will be steady again, right? So let me just, yeah. Now he's going to put it in the bottom. It's actually blocking the water to flow, so it's creating an overhead here. Now water will start flowing slowly over it. Here some funny things are happening that we go into it, but you can see after a while it reaches again an equilibrium. So it's again steady flow. Okay. Okay, great. So we have those two examples. Um, So formally, and for steady flow, we have the derivatives against times are going to be 0. And if it's unsteady, the derivatives are going to be different from 0, right? You should be noting that this applies in one point. So this is d dt at some point. Uh, let's say r equal, again, r equal r naught. Okay. So the flow at one part of your fluid could be steady, but in another part could be unsteady. Okay. The same goes with uniform, non-uniform. Uh, this applies also. This is evaluated. I'm sorry here, I'm just drawing on top of myself. This is being evaluated at some point, at some time, I mean. So if the flow changes over space, if the flow changes over space, uh, then it's non-uniform. And if it's constant over space, then it is uniform. Okay, but that is evaluated at one point in time. As you could see in this example, in the canal, in this lab canal, the flow was steady at some point and unsteady at some point in time, right? So keep in mind that you're evaluating this at different points or at different times, okay? But you should be able to tell apart steady, unsteady flow, uniform, and non-uniform flow. In the slides, there are a couple of examples. So let me just go back to them real quick. This is a typical example. This is flow down a pipe, down a tube. Okay. Uh, so as we saw before, if your flow is constant, then your velocity should be constant. It shouldn't change in time, and it shouldn't change in space. You know, you can easily tell that the velocity is equal to the flow divided by the area of this tube. So if the flow doesn't change at the boundary, at any point in this tube, you're going to have the same flow, and at any point, you're going to have the same velocity, right? So velocity doesn't change in space, therefore this is uniform flow. And if let's say this is water, and the water coming in doesn't change over time, then this also going to be a steady flow. So it's going to be steady uniform flow. This is a typical assumption for computing pipes and sanitary uh, how you say networks. Yeah, I'm being asked if I can put the links. Yeah, I'll put the links later on. They're actually pretty long videos. You don't need to see them all, but I mean, if you want, you can scroll through YouTube, and they're pretty cool stuff. But now let's say that you're closing a valve. Let's say a valve, you know, we normally call it. It's funny in English we call it upwind, which means you know uh, from the top. But in Spanish we call it aguas arriba. So in English we call it viento arriba. But you know what I mean is if you close a valve here before the pipe, and you start closing this valve, then you're going to start reducing the flow that is coming into the pipe, and therefore the velocity is going to be decreasing until it reaches a zero value. So that would be an example of unsteady flow. And now let's say that you have a pipe that has a reduction. You can all guess that if you have a velocity here, the velocity here in the thinner part of the valve of the pipe is going to be larger. Again, since the pipe is moving the same amount of water, here the velocity is going to be the flow divided by the area, and here the velocity is going to be the same flow divided by a smaller area. So the velocity here should be larger. V at R1 should be larger than VR R naught, right? So in this case, your flow is going to be non-uniform because you have different velocities in different points at, at one moment in time. Uh, and now if you start closing in, I mean, shutting down your flow, then the velocities are going to be decreasing in both sections of the pipe. But do realize that these velocities are also different. The velocity here at R1 is larger than at R0. So in this case, your flow is going to be non-uniform and unsteady. Okay. Hopefully that's clear. Should be, it can be. I don't want to repeat myself too much because this should be more or less easy to grasp. But if you have any questions, this is a very good time. Okay, now let me switch back to the whiteboard. So let me delete this a bit. So we have this classification. I'm gonna keep it there because it can be handy. And I'm gonna keep this. Okay. So now let me tell you about uh, different approaches on how to characterize flows. Okay. There's basically two approaches, and they should be complementary, and they should give you overall the same results, but they are nonetheless quite different, and people they can be confusing. Okay, so there are two approaches. I'm gonna write it down here. The this guy is called Euler, so this is the Eulerian approach, and this guy is called Lagrange. Lagrange. I don't know if you speak English, French, you can pronounce it better. But so we have the Eulerian and the Lagrangian approaches. Lagrangian with Y. Okay, Lagrangian approaches. What are these two approaches? Before going into details, think on a wave. Most of you, I'm assuming, have been on the beach. Most of you have been swimming on the beach and probably taken, riding waves. Maybe surfing, maybe, with your only with your bodies. But think of this: the same wave, the very same wave. Uh, I'm sorry. There was a question. Uh, I don't mind if you guys interrupt me. I try to read the chat, but I might miss it. So if I just pass your questions, uh, don't mind and just ask it loud. Francisco? What do you mean the first example? You can write it down, or you can just say it. The tubes. Okay. Let me go back because I think it's important. I mean, I don't wanna I don't want to move on if some examples are not clear. Okay, so this is the first example. Here the velocity doesn't change along the tube, right? Because I'm gonna write in the whiteboard. You should be able to see, but the velocity is the flow divided by the area. If the area is constant and the flow is constant, then the velocity is also constant. So this should be constant along the tube, right? So if the velocity is constant along the tube, then you have a uniform flow because it doesn't change over space, right? If on top of that, uh, the flow or the velocity or whatever uh, variable you have doesn't change over time, then it's also steady flow. Okay. So in this case, you have uniform, steady flow. Now, if you shut down a valve and the flow is slowly decreasing until it reaches zero, then you have unsteady flow, and the velocity along the pipe you can assume is more or less the same because yeah, this is a short pipe, so the wave moving from here to here is going to be more or less instantaneous. So it's also uniform, but unsteady, right? And in this case, it's not uniform because you're going to have V1, which is going to be Q divided by area 1. And you're going to have I'm going to use the same V0, which is Q divided by area 0. And realize that V1 is larger than V0, right? It has to be larger because area 1 is smaller than area 0. So in this case, your velocity changes over space. So it's non-uniform, right? And if you keep your flow, your Q constant, then this is steady flow, but non-uniform. And if you shut down your valve or you close your flow, then the velocities start to decrease over time. So in that case, it's unsteady, but it is still non-uniform because the velocity is not the same everywhere. Okay, I hope that makes it clear. Excellent. Any other questions before we move on? Okay, moving on. So what I was saying is, think on a wave, uh, think on the same wave, but you're watching it from the sand, from your towel. You know, you're tanning and you're watching the waves, and you can look at the wave and see how big they are, or how fast they are moving, or how they break, right? Uh, and also, most of us have been in water, uh, riding waves or trying to swim in the waves, and maybe being moved around by the waves. And if you have been pushed down by a wave, is a really is not very pleasant, right? So those are basically those two approaches. The Eulerian approach is trying to say, again, let me take a wave. The Eulerian approach is trying to say, okay, there is here some grid of points. Let's say this is Z, and I'm going to estimate the velocity on each of these points. Let's say this is going to be a mesh, something like that. So I'm going to have a mesh that's going to tell me the velocity at each point or the pressure at each point. Okay, so if I look here, I'm going to have a certain velocity that depends on x, z, and time, right? Whereas the Lagrangian approach says, okay, let's assume I'm the surfer here, okay, and I'm moving with the wave. So what's my velocity as I move through the wave? Okay, what's the history of this guy moving through the wave? You see, they both should be they should give you the same answer. I mean, the velocity at this point, regardless if you measure it from the surfer or from a fixed point in space, they should give you the same velocity, right? But it can be a bit confusing. So before going into more details, let me show you example, because normally, uh, for instance, numerical models, they tend to think on a Eulerian approach, on an Eulerian grid. Uh, we engineers tend to think, on a map, on a field, on space, that changes over time with velocities, for instance. Whereas in nature, a person riding a wave only feels the Lagrangian velocities, right? So let me show you uh, again. I know we're close to a break, so let me just show you these examples and then we can take a break. This one. So you should see this. Okay, this is a paper. You can actually look at it. It is in ResearchGate, and it has to do with velocity measurements in the surf zone. Does anybody know what a rip current is? If you don't know, it's not terrible, but they're pretty strong currents that occur in the surf zone, and they have to do with the direction of the waves. It doesn't matter for what I want to show you. But what they do is to measure rip currents is that they throw several drifters, and drifters can be very simple uh, floating bodies that measure velocities as they move through the fluid. Okay, so here you can see on your left several black points. Each one of these points is a drifter. The, in this campaign, they released hundreds of drifters, and they recorded the velocity and the position of each one of them as they move in the surf zone. Okay, the surf zone is where the waves break. The cool thing in this case is that they moved in circles, more or less circles. So they went uh, into deeper waters and then moved with the wave to the shore and then back. Okay, so they've been circling. And from those measurements, which are Lagrangian, because they follow the flow, you can compute here what I'm showing at your right, the Eulerian velocity field, which is which are the velocities over a fixed grid over space. And they were able to compute velocity intensity, and they computed this path of recirculation. It's quite technical, but here they were trying to. This is actually a rip current. You can see if you're swimming here and there are low waves, there's a big chance that you are going to be uh, tossed away and go into the ocean. Um, so you see, these are two approaches. One is more suited for measurements, like the Lagrangian approach is normally better suited for measurements because it's easier to measure, for instance, a drifter. Whereas the Eulerian approach is more better suited if you want to compute, let's say, the derivatives of velocity, and if you want to characterize the field of the flow, then the Eulerian approach is more better suited. But keep in mind that both should show you the same picture. Before we go to the break, let me show you. This is a Lagrangian drifter laboratory of NOAA. NOAA is a huge American how you call well I forget the name, but it's a huge American institute for ambient science, and they have a global array of drifters. So actually, you can see them, and you should be able, for instance, to pick one. For instance, this one in front of the Chilean coast, and it will show you how it's been drifting. So you see the velocity of this guy moving around is similar to the velocity of the flow that is feeling the drifter. It's not directly that, but you can make a good case for that. And if you have enough, you can compute, for instance, the velocities on the ocean, right? Which is easier to do than actually measuring every velocity at every point of the ocean. So you get a few points, and then you do uh, uh, your extrapolation. This is pretty much the same. It's a global drifter program, also by NOAA. Uh, is pretty cool. Here's this guy throwing one of these buoys or drifter into the water. These are different from the ones that I showed you in the surface measurement. And this is again a global array of buoys. And actually, you can pay for one. You can pay for one and you know be like a godfather of you can adopt one because this science is quite expensive. But the cool thing is that you can interpolate, for instance, velocities or wind velocity or flow velocities, or they also measure different kind of stuff like temperature of water or whatever. So okay, that was the difference between Eul- Eulerian, Eulerian and Lagrangian approaches. Um, if you have questions, keep it for the back until we return from the break. So let's take a 10-minute break and then we'll continue. Okay. Uh, should we continue? Hopefully, you're everyone here. Um, you should be able to see the slides now, right? So here's another example on this distinction between uh, Eulerian and Lagrangian. Uh, so here you're seeing about birds migration. Well, birds are not a fluid, but yeah, we can we can consider a flow of bird of some sort. But you could measure each individual bird, for instance, with these tracking devices, and then see their velocities and their trajectories, how they change over time, etc. Or you could, for instance, this I'm assuming is going to be a camera that is going to count how many birds are coming through a certain location. So the first approach would be a Lagrangian one, and the second one would be an Eulerian one, in which the Lagrangian you follow one specific bird, and the Eulerian one you measure at one specific point, and you see how the whatever variable in this case is changes over time. Yes. So hopefully that's clear. That distinction is clear. If you have any questions before we move on. Okay. So how do we visualize flow? Uh, if you have seen, again, water moving or a river flowing or any kind of flow, you know that flows are complicated. They have a lot of, uh, it's mainly due to turbulence that we're not going to talk about in this course. But flow can be very complex, right? So here there are three common ways to express flow. Streamlines, which is in Spanish is línea de flujo, uh, which is kind of an ideal path that a specific uh, parcel of flow is following. We have streak lines and path lines. Okay, we're gonna go into what each of those are. So it says here is streamlines are generally used in analytic works, uh, while streak lines and path lines are normally used in experimental work. And that's true at up to a certain point. I mean, streamline again has to do with the mean flow. So streamline or linea flujo again is the instantaneous line uh, tangent to the flow. Let me move to the next slide. So let's say uh, you have a parcel of fluid at one point, you know its location, and you know its velocity. And if you want to integrate the trajectory of that particle, then that line, that path that shows the trajectory at each point has to be normal to the flow, right? Meaning the flow at each point of this streamline is pointing in the direction where this particle is moving. So in a way, streamline is the derivative of the or the velocity is the derivative of the streamline, right? Now, formally, this means that if you take a small infinitesimal unit of this line of this geometric recollection that forms the streamline, if you express that as a vector pointing in the direction of the streamline, that vector and the velocity field have to be orthogonal, and that means that the cross product has to be zero, right? I'm sorry, I said orthogonal. What's the opposite of orthogonal? I mean, if the cross product is zero, they mean they're both pointing in the same direction. They're normal to parallel to each other. So if you know the velocity field, you can compute the streamlines, right? Because you only need to solve this. You can show this. You can show this that this relationship holds, but it's not very interesting to do it. But you can do it on your own. You need to compute this cross product and equate each component to zero in uh, in x, y, and z, or in I hat, j hat, and k hat direction. Um, so here's an example. If you know the velocity is this function, what's the distribution of the streamlines? Okay. Uh, we can try to derive this. Let me just stop sharing this. So basically, this is saying, okay, this is only in 2D. You see, the W velocity is 0, so we're gonna have this one, this coordinate system, right? And it says that for every point, the velocity here is going to be kx minus ky, right? If k is positive, this means that the velocity here is going to be that direction and in that direction, right? And you can see that, again, if k is positive, if we move to a point here, okay, so these don't have to be exactly the same, but if you move here, the velocity here is going to be actually larger, and the velocity here is going to be smaller than this one, right? So what's the shape that the streamlines are going to have? Okay, here what we need to do is just use the equation in the previous slide, right? And let's say that the x over u has to be equal to dy over v. And we know these velocities, so the x over kx has to be equal to the y over minus ky. You can see actually we can remove k because it is at both sides. So let me just remove it. And if you integrate this, you're way more familiar with calculus than me, but this is actually a logarithmic. So this is the natural logarithm of x. This is minus natural logarithmic of y plus a constant, right? And this constant you can express as also as a logarithm. So it's a log of some other constant. Yes. So I ran out of space. I'm sorry. Um, uh, Give me a second. Okay. So you can put this together. Give me a second. So you can say that the log of x times y, because of the minus, has to be equal to some constant that we don't particularly mind, k0. And if the log of x times y has to be constant, then x times y has to be also constant to some other constant. So x times y has to be constant. And you can show that, well, you can solve here y. So y is some constant over x. And that's just some function like this, right? And depending on the constant, you're going to have different paths. So this function here is y over whatever constant over x. And this value is going to change depending on your particular problem. Here we weren't given any initial conditions, and we really don't know what x is. But if you know the position at the beginning of one particle, you should be able to compute the rest of the streamline. Okay. Um, okay, back to the presentation. So to derive the streamlines, you need to apply this equation. It's, it's not an equation, but it's actually three separate equations that you get to these relationships. In this case, we were uh, busy with set, but could be important in another case. So yeah, here's an example. So you get this kind of streamlines. Now the streamlines, again, they are an ideal representation of the flow. In reality, flow is way more chaotic. So normally in a lab, for instance, you're going to have path lines. A path line is nothing more than the path that one particular particle traveled. So you somehow put ink or dye in one particle, or you track it with, I don't know, with a camera. And if you can record every position of that particle, that's going to be a path line. All right. And different particles are going to have different path lines. Uh, but if you analyze them all together, you might be able to say something about the flow. I won't go into much detail here. And finally, streak lines is similar to path lines, but here we're going to be measuring all particles that cross one particular point. So several particles cross one point, for instance, here. And you can see that later on down the flow, each particle follows its own path. So it's similar to path lines, uh, but it has the added complexity that all particles have to pass for the same point at some moment. Okay. If you have an ideal flow, and if you have a steady flow, then all of these three are they converge and they show you the same picture. Okay. If you have no turbulence and if the flow is steady, then path lines, streak lines, and streamlines are going to show you the same picture. We are normally going to focus on streamlines because it's one way to represent the flow that we can deal and understand with math. Okay. Was that part clear? Because we're going to move to some more confusing stuff, or potentially confusing stuff. Okay. I'm going to assume it's pretty clear. Okay, what I'm about to show you is at the core of most fluid mechanics and hydraulic courses. So I would argue that this is the most important concept of this unit uh, because it lets you build and actually create later on the Navier-Stokes equations or the Euler equations. So bear with me. It's can be a bit cumbersome, but I think it's really important. Okay, so far we've been talking about velocities. We've been talking about how to differentiate flows if velocity changes over time or over space. Uh, but if velocity changes over time, that means that velocity uh, might be accelerating. Otherwise, it shouldn't change, right? And as you can imagine, accelerations are pretty important if you want to compute forces. Uh, so the acceleration of the flow is a pretty important thing. I showed you already that if your position is x in y times in I mean, times y in j times z in k, then your velocity, these are vectors, your velocity is nothing more than the derivative of this, and that's we're going to call, let me just show you, this is dx at dt uh, in I times, these are actually not partial derivatives, these are, bear with me, these are dx at dt I times dy at dt j times dz at dt in k. And we call this u, v in j, and w in k, right? But if we want the acceleration, well, you can imagine the acceleration is also going to be a vector, right? And that's going to be the derivative, uh, the derivative of v with respect to time, right? And simply put, that's going to be the derivative of u with respect to time in I times the derivative of b with respect to time times j times the derivative of w with respect to time times j. Okay, so far it doesn't look different from this first step, from position to velocity. We already did this, so what's new here? What's new here is that the change of velocity over time also depend on the change on position. You can think of a fluid, of a parcel of fluid that is moving through the velocity field. Uh, as it moves, velocity might be changing because because it's a non-permanent or unsteady flow. But velocity might be changing also because you're moving, because you're passing from one position where velocity has one value to another position where velocity has another value, right? So these derivatives are a bit more complicated. Okay, they're not rocket science, but you need to pay attention. So let me let me I have space. Let me write this here. Let's take just this first derivative. I'm gonna use the other color there. So the u at dt, as I said, it might depend on x, y, z, and time. So it depends on many variables, and uh, at its own turn, x might also be a function of time, and y might also be a function of time, and z might also be a function of time, right? So this derivative, uh, I'm going to write it here because it's going to be a bit long. This derivative is going to be the partial derivative of u with respect to time plus the partial derivative of u with respect to x times the actual, or the not the partial derivative of x with respect to time. This comes out through the chain rule that you should know from calculus. And then you keep on doing this on every other variable. So you have the partial derivative of u with respect to y times the derivative of y with respect to time. And finally, the same with respect to z times dz to time, which is actual derivative. Okay, this is called a total derivative, right? In fluid mechanics, we normally call it the total derivative or the material derivative, and it's composed of all of these guys. Now, by definition, the derivative of x over with respect to time is u. Yeah. And the derivative of y with respect to time is v. It's actually the velocity of the flow. So we can rewrite this as the total derivative, as the partial derivative with respect to time times, we normally put the velocity in front, times u, du at the x, times v, du at the y, times w, du at the z. If any of you follows hydraulics later on, you're going to see this equation over and over again. Okay. You can show for the rest of the velocities components that you get a similar result. Okay. Um, let me just write it down here. So you can show that the v at the t is going to be similar. It's going to be the partial derivative of v with respect to time times u dv with respect to x times v dv with respect to y times w dv with respect to z. And similarly, the w with respect to t is dw with respect to t partial times u derivative of w with x times v derivative of w against y times w derivative of w against z. Okay. Is this clear so far? I know I mean, you can look at these equations in the slides, but I think it's important to show how you get to them for the following. If you have questions, just interrupt me. I do feel like I'm talking alone most of the class, so uh, any question is welcome. Let me just put this here so it's a bit clearer. Now, this is the basis of why hydraulics are complicated. And it has to do with this set of equations, with this acceleration part. Because if you remember from you took a course on partial derivatives or something like that, you might be able to realize that these terms here are nonlinear terms. You have a derivative of one velocity of one variable multiplied by the same variable. The same here and the same here. So these terms turn this acceleration into a nonlinear function. And as you might know, integrating nonlinear equations can be very, very challenging. Now, if your math is good, you might be able to see a pattern here. You might be able to see, I'm going to highlight it like this. You might be able to see it here. It's a U, here's a V, here's a W, which is the velocity vector, right? And here you have derivatives with respect to X, derivatives with respect to Y, and derivatives with respect to Z, right? So if your math is also good, you might be able to see, and if you know that I'm running out of space, but you might be able to see that this is just your vector V and the dot product with the operator nabla applied to the vector V. So all of these three equations can be resumed elegantly as this, right? And nabla, if you know, this is the operator to d at the x on I plus d at the y on j plus d at the k at the dz. Okay, right? And this and this part here is the temporal derivative, the partial derivative against time of the vector v. Can you see this? Is this clear? It is pretty important because, and this is the total derivative. So this is the total derivative or the material derivative of the velocity, which is the acceleration, is due to this part here is called local acceleration, and it has to do with the change over time of the velocity field. And this part here is called convective acceleration. Convective acceleration. And it has to do with the change of the velocity field over space. So again, to repeat, the acceleration of the flow is due to two effects. One is the change over time of the velocity, and another one is the convective part, is a change over space of velocities. And this convection creates an acceleration. For instance, if you think on the previous example, let me just delete this. If you think on the previous example, we saw, okay, let's say a pipe. Here we had a smaller pipe, right? And you have a flow coming in, right? And we said this here the velocity c, here it's q over a0, and here the velocity is q over a1, right? And v1 is larger than v0. So here you can think, you can realize the water coming here, flowing through this pipe at this point uh, near the exiting point, is going to have to accelerate locally in order to enter this part. So around this change in shape, you're going to have a local acceleration, and that local acceleration is not due to change of the velocity over time, but it's due to change of the velocity over space. So here you have a local acceleration due to these convective terms that can be expressed as a vector with this expression, but you can see it, uh, you know, for each velocity. So what's happening here is that the horizontal velocity is changing into vertical velocity that didn't exist before, and then the horizontal velocity is increasing, right? So you should be able to see that there is an acceleration, and if you have accelerations, you're going to have forces. We won't go into that now, but keep in mind that if you have accelerations, you're going to have forces, and flow accelerations are due to these two components. Is that clear? Uh, uh, can I make it clearer? Just to repeat myself, the change in velocity here is going to be equal to the local change on velocity, the local acceleration, times this advective term. You can see that if you have steady flow, then this local acceleration is null, is zero, right? Which is the case uh, in this pipe reduction. Whereas if your flow is permanent, then this guy is zero, and your only change is going to be due to changes over time of your flow, or or your conditions. Okay, so uh, it's nice that the mathematical representation matches the division that we did before. Okay, like I said, I think this is the basis of this part of the course. If it's not very clear, just give it a thought, and maybe we can discuss it later. But this is going to be the basis to compute the continuity equation, which is the conservation of mass, and the conservation of momentum. And those two equations are the basis for, for the Navier-Stokes equations, which govern the motion of fluids. Um, so, okay, if it's clear, I'm going to ask again, any questions? Okay, no questions. Great. Let's move on to conservation of mass. Okay, I'm going to. I'm not going to keep this. Conservation of mass. As you know from previous courses, uh, when you're dealing with a physical system, you conserve it, you keep the total amount of mass, and you keep the total amount of energy, right? Uh, and momentum. We're gonna start that analysis with the case of mass, and we're gonna do something similar to what we did for pressures a few weeks ago. So let's again think on a very small parcel of fluid, okay? And for convenience, we're gonna place our little parcel right at the center, just so we don't have to draw too much, right? Okay, and this, okay, and this is going to have dimensions uh, of dx. I'm sorry. So I'm gonna call this dz on the up. This guy here is gonna be dx, and this guy here is gonna be dy. So this x, y, z, right? And we're going to assume that we have flow on this fella. Uh, so let's start with the let's assume that on this side you have water coming in, right? Uh, okay, I messed up the directions, but it doesn't matter. So let's say we have water coming in with a certain velocity, and let's say that we have a fluid with units with density rho coming in. Okay, so okay, I'm gonna follow the convention that I just draw. Is slightly different from the one on the slides, but it shouldn't matter. So you can easily see that the water, the amount of mass coming into the this volume is going to be, again, if this is x, y, and z, then the velocity field is going to be, let me just draw it here. It's going to be u, v, and omega, and w, right? At any point, these velocities depend on the point on time. So at at this phase, at one particular time, the water coming in is going to be equal uh, to rho times v, right? times the area of this square of this, I'm going to highlight it in red, times this area, which is dx dz, right? So that's the water or the mass coming in. And let's take this other side. Here we're going to have mass going out. Right? And the mass going out is going to be uh, is going to be the velocity at this side, which again we can approximate using Taylor series expansion. So we know the velocity at this point, and the velocity here is going to be the velocity at this point times the derivative. So the water coming out is going to be rho v times the derivative with respect to y in this case of rho v times the distance it traveled in y, and all of this times the area of this square, which again is dx dz. All right. Or here I'm just putting myself ahead of myself. So, and this is, let's say this is in and this is out before we equate anything. Okay. So you can see it in the slides. Basically, what we're gonna say is that the change of mass over time on this particular cube has to be equal to the change in flows, right? Because mass is not being created anywhere in this cube. There might be cases where, for instance, if you're talking about bacteria, it's going to be a reactive process here in which bacteria increases proportional to the concentration of bacteria, something like that. Or you can have decay of matter. So let's say you have, I don't know, dissolved matter in a tank, and that dissolved matter is being eaten away by, again, bacteria. So in that case, the mass is changing. Okay, we're going to assume that there is no creation and there is no destruction of mass. So the total change of mass within this volume has to be only due to the flows of mass through the phases, right? Uh, so we can express that as follows: the total the change of mass in this volume of control is going to be the integral of the derivative of rho over time over the volume, and that uh, plus the outflow minus the inflow should be 0. Here the conventions matter, but in this case, since everything is going to be canceled out, it's not very important. Now, since this is a very small volume, we can assume that the density of whatever this is, this could be air, or this could be water. The density should be more or less constant within the volume. So this part here, we could approximate it as the derivative of rho over time times the volume itself, right? Plus out minus in. And the volume itself is just dx, dy, dz, right? So we're assuming there are no sources, there are no losses of mass, and all the change of mass depends on the flow. Um, So if we continue what we did, this please do realize that this is only in the y direction, but you could do the same for every other direction. So you should do the same for this. You should do the same for this, right? But let's continue with the y direction. So here the flow going out is going to be what we just put there. Maybe I'm going to run out of space, but well, bear with me. It's going to be uh, the, the derivative of y of rho v times dy plus rho v times dx d oh, times dz minus rho v dx dz. This should be 0. Okay, this is the analysis on the y direction. And I'm going to delete this. Sorry, I'm just deleting what I just wrote down, but you can see that this part is going to get canceled with this part. So what you end up is that the rho dt times dx dy dz has to be equal or plus d rho at dv at dt times the same dx dy dz. This should be 0, right? And that's, is nothing more than this. Is that clear? Well, and if you do the same for the three directions, you're going to end up with this equation. The total mass, the total change is going to be rho dv plus d at dx, the rho u plus d at dy, rho v plus d at dz, rho w. This should be 0. And you can think of this as rho u is the flow of mass in the x direction. So this is the rate of change. This is the difference between what's coming in and what's going out in x. This is the difference between what's entering and getting out in y, and the same in z. So the sum of all of these differences has to be the total change in density, and density over a volume is just the mass. So you can express this in a more fancy mathematical way, which is this one. So the local derivative plus the nabla operator of rho times the velocity vector. This has to be 0. And again, this says that the local change in density, which is the local change in mass, has to be equal to the advection of mass. The advection is nothing more than the transport of mass through the boundaries of your control volume. Okay, it's a pretty important equation. It's going to be the basis of the Euler equations and the Navier-Stokes equations and the Bernoulli equation. So this is pretty important. Uh, Realize too that we haven't said anything about the flow. I mean about the fluid. We haven't said if the fluid is compressible, is not compressible, or if the flow has any characteristics. So depending on the characteristics of the flow, we can reduce this equation to something more manageable. Okay, so let's take a break now, and when we return in 10 more minutes, we can discuss how we can simplify this in certain cases, uh, and we can talk about yeah, some questions that you might have regarding the next midterm or the coming homework. So hopefully I'll see some of you after the break. Okay, see you in 10 minutes. Okay, hopefully many of you are back. So I was being asked if this period is going to be only to answering questions. What I want to do in this final minute is to wrap up this mass conservation, the continuity equation, and show a couple of applications. Then I want to show you a bit on what you're going to have to do for the homework, for the coding homework for this weekend or for this next week, which I think is going to be useful for the test next week. And then we're going to have a minutes for the test. We could be questions, or if you want, we can look at an example. Uh, okay, so this is the continuity equation or the mass conservation equation. Basically, this is a mathematical way to show that the mass of the fluid is conserved. Now, if you remember what we said about classification of flows, you can see that here there is a derivative of time. So if we have a permanent flow, this should be zero if permanent, right? So if your flow is permanent, you only have the advection part of the equation, right? Uh, Also realize that if you have uh, an incompressible uh, fluid, then rho it's pretty much constant in time and also in space. So if you have an incompressible fluid, uh, then the rho at dt is also zero, even if we have unsteady flow, right? And if it's constant, then you can pull it out of this nabla operator, and so if it's constant, you get this, and you also get that you only have your nabla operator over velocity. This has to be zero, and this is a classic equation of du over dx has to be plus dv over dy plus the omega times dz has to be zero. This is sometimes called the rotor. I don't know if that's the name in English, or the vorticity. Okay. No, I'm sorry. The vorticity is nabla, the cross product. I'm sorry. But basically, what this is saying. So I'm not sure about that. So maybe I messed up the concept. But basically, what this is saying is that in if the density doesn't change, if the density is constant in time and space, then all change in mass has to do on how the velocity is aligned. So let's say we have a 2D flow. So let's consider this is zero for a moment. Basically, this is saying that the change in one direction has to be equal and opposite to the change in another direction. Okay, if you take a tube that moves this way, here you only have u velocity, and here you only have v velocity. So the change of u over x has to be equal to the change of v over y for this to be conserved. Okay. And normally this is the equation that we use for water, for fluids like water. Okay, because we know rho is pretty much constant. It doesn't change over time. It doesn't change over space. But if you don't know that about rho, then you have to use the full continuity equation, in which uh, how rho changes over space is also important. Okay. Okay, great. So that was it. Next week, we're going to see the conservation of momentum, and we're going to end up with pretty useful equations to characterize flows. And actually, we're going to wrap up this fluid kinematics next week. We're going to take 2 weeks instead of 3, because I think we can do it. Are there any questions about today's lesson So what we saw today: permanent, unpermanent, I mean steady, unsteady flow, uniform, non-uniform, Lagrangian versus Eulerian approaches, uh, conservation of mass, and the acceleration, how you express the acceleration of flow in this uh, local and advective terms. For continuity is the same. You have local change in mass and advective changes in mass. So for the acceleration, it's the same pattern. That's the summary of today. Any question of that? No, it's pretty clear. Okay, great. Everything clear. Excellent. Good to hear. Hopefully, uh, everything will be very clear in the coming exam, right? Okay, let me see. Let me show you now a bit about the incoming homework. What you're gonna have to do, I mean, with in the statics part, we talk about pressure distribution, which is due to the weight of the fluid, and we saw how to compute forces, right? Forces on flat surfaces, on submerged bodies, and on floating bodies, right? If you and we show you several equations to compute different stuff, but if you were paying attention, you would have noticed that all the equations are derived in the same way. So it's the integration of the pressure over each uh, individual small pieces of surface areas. Let let me put a little light here. Okay. So what we're gonna ask you in the homework, in the coding homework, is that you actually go and do a numerical integration of pressure in a general form. And we're gonna ask you to apply that general approach into flat surfaces and submerged bodies and floating bodies. Uh, Also, you should be able to. I mean, I'm gonna give you the details probably on Thursday, but I want you to know in advance. So hopefully you can prepare or read a bit. And now I want to show you a very short example on how to do numerical computations. It might seem numerical integration. I mean, it might seem more complex than what it is. It might seem a bit, if you're not very familiar with coding, might seem a bit frightening. But let me show you that if you can do a loop, a for loop, then you can do numerical integration. Okay, so let me show you my screen. And okay, so this is a typical example. Let's say you have a half circle, a half circle, and you want to compute the area of that. Of course, you know the area of a circle, which is b r square, and a half circle is just half of that. But what's the centroid of a circle? Normally, when you would say, but you're going to give me that in class. Yes, we're going to give you that. But how do you compute the center of mass of a circle, of a half circle, or of whatever shape? And if you have been paying attention, uh, you should be able to see that it's actually pretty easy. So let me show you how you would code that. So let's say you have uh, let's say you have I'm sorry. Let's say you have a radius, and we're gonna have a 1 meter radius, and we're gonna define um, half a circle. Okay, and what we're gonna do is that we're gonna split this area into small pieces. This is what actually you have to do in your homework, and how you normally would do this kind of thing. So let's say we're gonna split this area in small pieces. Let's say in and the number of theta uh, pieces we're gonna take is 20. Sorry, 20, and the number of radius splits that we're gonna do is 10. Okay, and these are gonna be your parameters. Okay, and now what you normally do is that you compute a mesh, or you compute just the corners of each individual uh, uh, individual small area, in the same way as you would do if you were integrating this numerically. Okay, so let me compute the corners. So let's create a couple of vectors. Theta corner gonna be this function. Uh, this function just creates a vector, from one value to another, uh, that has a number of elements, and it's theta. We can do the same with the radius. Here to radius and a radius, uh, and this is going to be none. Okay. But this creates, you can look at them. This creates a vector from 0 to 1, right? But we want to mesh, and a mesh for these corners. We're going to call it same variables, but just like that. And you create a mesh with this function. So I don't expect you to know this, so that's why I'm showing you. I'm showing you this now. Basically, this function of numpy create a mesh if you give it to vectors. So now we give vectors corner. Okay, and this is going to create mesh. You see, R is actually has 2 dimensions now. Okay, you can see the shape of RI. It creates a mesh with the 2 vectors that you just created. Okay, and we can compute the actual positions in the Cartesian grid for this is R sine p cosine of theta y, and in y it's going to be similar, right? But just sinus. Right. And okay, so that's the position of each panel, right? But you can see that that's the position of each panel, but we want the positions at the center of of each panel. So what we can do is similar stuff. Oops. Oh, okay. Similar stuff, but for the center points. Okay. So let me just copy this. Center of the panel. I'm gonna say center, and here we're gonna take actually we're going to take the midpoint of 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 this of the vector of the corners. Corner 1 on, all minus 1. So this vector theta center is just computed the mean point of the of this vector. Yeah, and we can do the same with r, with radius. I mean, for the corner 1 on plus half per corner, all up until the last one. Okay, and we're going to code the center with j's instead of y's. Okay, and the same with the positions. Now, this might seem more complicated. I'm sorry. Yeah, that's right. Than it is, but you can follow it along. I mean, it's not rocket science. And here comes magic part. Let's say, what's the differential values of each of these cells? Okay, so delta theta or d theta is going to be theta max divided by the number n theta minus 1. Why minus 1? Because this vector actually just shows you the corner. So if you have two corners, you only have one element. If you take in enough elements, it shouldn't matter, by the way. So it's not very important. I don't mind that you are super good at doing numerical calculations. I don't mind the truncation error or that kind of stuff. You can learn that way better in other courses. But I do mind that you get the idea. Okay, and the delta radius, the delta r or dr is the radius divided by the number of units that you have in the radius minus 1, same as before. And how do you describe the area of this differential area? Here, if you realize we're working in polar coordinates, so each area has a different value, right? And if you've written everything right and the units are consistent, you should be able to show that the area of each small infinitesimal division should be r dr d theta, right? That you should know that from math. If this was a plane, then it should be dx dy, right? Um, only that for each element, dx and dy are going to be different. So it's easier to express in polar. So it's going to be, I said, j times dr, which we know that's actually constant times d theta. So here uh, this changes over time, and this is a cool part, I think, at least. The total area. Let me just call this the area. The total area is just the sum of all the smaller areas. So if you have a vector or a matrix where you put uh, the all of the small values, then the integral is just the sum of all of the values, as long as the units are right. So I think it's easier actually than just integrating if you don't remember, the integral of cosine or something like that. Uh, Here you only need to express the delta area as it should be, and then the total area is just the sum. That's, I think, one cool thing. And the centroid position, if you've been paying attention, the centroid position is nothing more than the position of each element times the delta area, right? You need to sum over this. Sum over all of those, and you divide to the total area. Wait, let me just, I'm messing stuff here. Okay, right? With y is the same thing, but just using y. So let me see if this runs. Was that clear? Because you're gonna have to do something pretty similar in your. No, but you can watch the video again. uh, because I'm not interested in copy pasting code, but I want you to understand. Here we're only integrating the areas, right? But then if you're looking at pressures, then you know that the force in a small area is going to be equal to the pressure at the center times the area. Okay, so let me just copy the code to show you this, because I know this can be a bit abstract. Let me see if this works. Yes. So you see here, you don't need to remember everything here, but here this function is plotting the mesh. So here we're giving it the corner locations, and we're painting it uh, with different colors divided depending on the area. So you can see all of this, the outer rim has one color, and then it gets smaller because the inner space have smaller areas. This code here just points the center of each element. This is actually the color bar of this one. So, and this one here plots the center of the total centroid, which is here, which is where you should expect it to be, right? At the center. Now, here's the cool part. I think it's cool, at least. If you're doing this right, you could put this into a function. It could be nicer, but you could compute this, for instance, for a quarter of a circle, right? So if your functions are right, and we never really said this is going to be half a circle, so it could be a quarter. And the position is there. You could compare later on if the position is right. Okay, uh, and you could also, well, let's say here we have area. This is the area, and we could complete the we could compute the theoretical area, right? The theoretical area should be mp pi times radius square divided by 4. Uh, Radius. You can see the same, right? So I don't know. You might think, well, this is more complicated than it needs to be. But like I've said before, in reality, you don't get nice geometric shapes, right? In reality, you get, if you have a dam, then the shape of the dam is going to be awful. It's not going to be a nice triangle or whatever. And again, here the part where you're going to have to show that you understand the pressure distribution is going to be something similar to this. So here's only the area, but where you're going to have to integrate, for instance, if the force, then you're going to have to integrate the force at one particular small element, and then sum over all elements, right? And it's also cool, you can change, I don't know, if you take a uh, larger circle, then this should keep on working. Yes. Anyway, this was an example. I think it was better if I showed you here rather than in a separate video. So just to summarize, what you're gonna have to do in the homework is to integrate the forces over an arbitrary surface. Okay. So yeah, and do a numerical integration, more or less based on what I showed you here. Any questions about this? Let me stop sharing this. Maybe I will share you the code. I don't know. Yeah, I think I can do that. I really want you to do well in the homework, um, but I don't want to give it away, right? So I want you to work for it, and I want you to help. The homework helps you uh, to prepare for the coming test. So we have a couple of minutes. If you have questions about what I just showed, or about the unit 2 on statics and pressures. I'm being asked if in the recitation there's going to be something similar to homework. No, there's going to be something on pressure and forces. Uh, but no coding. I mean, what I just showed you now is the only coding help that you're gonna have, because it's really not more complicated than that. But again, you should have a look at how to compute forces on a flat surface, on a submerged body, how to compute the point of application of the force. If you look at the derivations, it's always the same. At the end, you might end up with an equation that you can readily use. But for instance, those equations have uh, the how it's called the moment of inertia of an area. We You could compute, for instance, the moment of inertia of a quarter of a circle. Uh, but you see, if you do a numerical integration or an actual integration, let's say a calculus one, you don't need it, right? Yeah, I think recitation this Thursday is going to be about Unit 2, uh, considering that we have the test next week. And next week, Thursday, that recitation might be about Unit 3. So this Thursday, you have your last uh, examples on Unit 2. Next Monday after the class, I mean, in this very same hour, we might discuss your final doubts uh, on Unit 2 or Unit 1. So that's it. I think it's not a lot of material to cover. You should be able to understand it well. Um, but realize, be aware that there are many questions that can be asked. So you should feel comfortable computing forces, understanding how pressures distribute, um, and how to compute, the resultant points uh, for any given surface. That you should feel comfortable doing that. If you're not, go ahead and have a look, because yeah, that's going to be a big part of the test. Okay, any more questions? No. Okay, so be aware. Probably on Thursday, I'm gonna upload the homework. I'm gonna have until following Monday to turn it in. Um, yeah, don't copy. I'm gonna say that as clear as I can. Try not to copy. We're gonna have different exercises for depending on your student number, so you shouldn't be able to copy much. But yeah, just as a recommendation, if you want to learn and understand, try not to copy the work of your fellow students. Try to do it on your own. Okay, if there are no more questions, that would be for today. Thank you very much for for the ones that endured these 3 hours. Every Monday we're fewer and fewer, but yeah, it is what it is. So thank you guys. Have a nice week. Okay, cheers.